Good morning, everyone. Before I start moving into using solid parts and solid elements in ANSYS Workbench, I'll be happy to take any questions about the previous homeworks.
I'm still having an issue trying to figure out how I can find the axial stress in certain numbers. Like, I don't remember what probes to put on there or whatever else.
Okay, specifically for axial stress.
Yes.
Okay, so let me answer this question here about axial stress. So I'm going to open here one of the beam problems that we've done and remind you is where to look for axial stress. Now, when we say axial stress is referring to the normal stress. So the stress along the axis of the member is the normal stress, sigma x, correct? So when I look at this simply supported beam, this is the example we did in class. As you can see, because this goes in bending, the bending moment is going to result in an axial stress or a normal stress, sigma x along the x-axis, that is equal to minus mz over iz times y. So this is bending axial stress. We can also call it bending normal stress. There is also an axial stress due to a normal force that, according to the terminology we are using in ANSYS, would be called direct stress, or I can call it also axial / normal stress. This is also a sigma x, but will be equal to the normal force divided by the area. Is that concept clear? Now, I would also like to mention that the stress sigma x could be a result of an mz or an my, if I have double bending, or both combined. So I can come here and add to this plus my over iy times, in this case here would be z. So where do we find these in ANSYS, the results for these? When I come here to the solution, and look at under tools, under toolbox, there is a beam tool. When I select this beam tool, it shows here in the outline. When I expand it, I get the direct stress and I get the minimum and maximum combined. Why is there a minimum and a max? Because when we looked at the stress distribution from the MZ, it was linear distribution. If MZ was positive, I had maximum tension. So I can think of this as the max. And at the top, I had maximum compression. So here was tension and here was compression. So this would be a minimum because it's negative. Depends on the section. The minimum and maximum may have the same magnitude, but really it depends where the centroid is located along the section. So when I'm looking at ANSYS here, this is the reason I have a max and a minimum. But be careful because these are combined stresses. So they're not the bending stresses. If I want to show the bending stress, I would come here and go insert, right click and go to the beam tool, stress, and then I can put the maximum bending. So now I have a maximum bending, a direct stress, and a combined. The combined is basically the sum of these two. So this is the combined. Sigma x would be equal to n over a plus the minus mz over iz times y plus the my over iy times z. Okay, so back to your question. So what is the axial stress that is referring to? If the problem is asked you for just axial stress, it is referring to the direct. The bending stress will be this one. And combined is both of them added together. Does that answer the question?
So using the beam tool and everything, it gives you the combined. So it gives you both of them.
No, under the beam tool, not only the combined. I can get the direct stress by itself, which is from the normal force. I can get the bending stress by itself, and I can get the combined. So I can get all three of them.
And then if we just want to apply that to a specific, like if you have multiple portions of the member, like how do you apply that to just a specific one?
When you say multiple portion, like different sections?
Yeah.
We're not applying it, but we're finding it. Like if I come here and solve, right? So this is the solution that I get. If I want to find the stress, like I'm looking here at direct stress and it's all zero because I do not have a normal force. But if I look at the bending stress, I'm getting the maximum where my moment is max, which makes sense. Okay. Now, if your question is about how I look for the stress at a specific point, is that your question? Yeah, I can use the probe. I can come here and look at any given point. That's one way of doing it.
The same with if you put maximum or minimum, will it just highlight that point?
Correct. It will just show the max. Okay. So the max here is right at the center. Now, how do I know the value of the max? It's showing here on the fringe plot. So you see here, it's 1.5 e to the power 8. That's my minimum, my maximum, sorry. If I go minimum, the minimum is at the support and is 0, which makes sense for a simply supported beam. Does that clarifies it all? Still have any questions? Good. Any more questions on using beam elements?
Just based on the homework for the PDF that's required for the results, how do we format them? It's the last time I got one.
Okay, basically for the PDF, I'm simply expecting, like if you have this shaft problem, I would like to see like RO, the reaction at O, the reaction at C is equal to the M maximum, the maximum bending moment. If it's asking for deflection specifically in the y direction at a given point, YA equal in inches, of course. So simply a list of all the numbers and where you find them. And the purpose of that, it is sometimes not difficult to someone to follow instructions and run ANSYS. But really the more important is how do I interpret the output of my answers? I want to be able to relate the results I'm getting to my engineering problem, right? Okay. But if there is any concerns about the grading, please bring it to my attention.
Yeah, I didn't do anything close to that, so it was okay.
Okay. Okay. But anytime, if you have any concerns, please let me know. Good. More questions. Let's always make sure we have good understanding of what is required and what is expected. Speaking of that, I have pushed the quiz and homework because this week we have the fall break and we had a quiz due on Tuesday or scheduled for Tuesday. I think it would be nice to come back and meet again before we do the quiz. Should you have more questions, we'll be happy to take them, and then we'll do the quiz on Thursday. Also, the upcoming, there is a simple homework that you should be able to complete today after the class. Will take you a few minutes, which is homework 7. But homework 8, I also pushed for Thursday, so we have time after we come back from the fall break. So this way, you should have a real break and enjoy some time off while staying well and safe, right? If there are no more questions, I would like to move on with the topic we have for today. So my goal today is to move you from using beam elements, where we had to take these solid parts or 3D parts and simply use a model that is linear using beam elements. We want to go from using beam elements to being able to use the actual 3D CAD or a solid part and discretize it, break it into small pieces. But these pieces are not going to be linear beam elements. They're going to be solid elements. Okay, so today I would like to introduce in ANSYS how we work with 3D geometry and solid elements and still be able to get the same results that we have done in the past. So let me close this project, start a new one. So I'm going to come here and say new. Do you want to save it? No. Okay. So this will start a new project. I would encourage you all to launch ANSYS and work with me as we start working. And today we're going to focus on axially loaded members. And I'm going to go back to my first class example. This problem we have solved using equations of equilibrium and compatibility equations, as you've learned it in solids. We have solved it using the finite element procedure and matrices. We have solved the problem in ANSYS Workbench using beam elements. And today we're going to solve the very same problem using 3D CAD geometry and ANSYS solid elements. Okay, so just to remind you, we have a part here made of 2 cylinders that are connected together at B. AB is 10 inches long, BC is 12 inches long. AB has a diameter that's smaller than that of BC, and we find the diameter of AB to be 0.178412 inches, and the diameter for BC to be 0.21851 inches. This is made of a material that has a modulus of elasticity of 10 million PSI. So it's not made of structured steel. And we want to learn how we can model this part and create it as a 3D geometry in ANSYS. And once we do that, we should be able to create geometry, assign material, define, generate a mesh comprised of solid elements, define the boundary condition, apply the loads, look for a solution, define results, and know how to get everything we were looking for. So the question becomes, what is it that we're looking for? We're looking for wall reactions, the reaction at A and the reaction at C. We are looking for how much point B is going to move. We are looking for when we did this earlier, we said we're going to look at the forces in the member AB and BC. We're really doing that so we can find the stresses within AB and BC. And just to remind you, we found that AB was in tension and BC was in compression. We still want to do the same using solid elements. So let's get started here. So I'm starting here with a fresh new project in ANSYS Workbench. Before I jump into that, I want to make sure I have the correct units. So I will go to units, and we are clearly using US engineering, pound, inches, seconds, etc. So these are the units, and we want to make sure that we display the values in the project units. I am going to give the project a name, so I'm going to save it as, and I'm going to select my 2021 full directory, and I'm going to call this first solid class example, specifically for axially loaded. So that's going to be the name of my project. Within that project, I am going to use a static structure analysis system. So I'm going to come here and double click on static structure. So we have a static structural system, and we have engineering data that only has the default structure steel material. So the first thing I want to do for engineering data, I'm going to double click on that, and I want to add the new material. So engineering data, under structure steel, I'm going to come here and say class material. And I have the question mark. I need to define from the toolboxes the material model. How is this material going to behave? So we're always working within the linear elastic, and it's an isotropic material. So I'm going to pick isotropic elasticity, double click on it. It will bring here properties of outline, row 4, class material. So under isotropic elasticity, it's prompting me to input the modulus of elasticity and Poisson's ratio. You see the units are in PSI, and I want to put 10 million or 1 e to the 7. For Poisson's ratio, we're going to use a 0.3. Enter. So this takes care of the class material. I'm going to toggle back to the project and looking at the project schematic. I have my data, my engineering data. Oops. Sorry for that. So we have our engineering data. Engineering data. Next step would be the geometry. Be careful just to select geometry, but do not double click on it, so you don't accidentally launch space claim. You want to right click when you're selecting geometry, and you want to make sure to select new design modular geometry. So I click that, and this will launch design modular. It will launch design modular. So here comes my design modeler with the 3 default planes that I can turn on. So I have the XY, ZX, and YZ plane. For our axially loaded parts, we want the axis to be oriented along the X axis, like we did before.
but we are going to create a solid piece. And from your CAD experience, creating a solid part, we can use extrude, we can use revolve, we can use a sweep, we can use a thin loft. Skin loft. So what we're going to do here for the part, we can create it either using revolve or extrude. We're going to simply extrude 2 sections to create the part that we analyzed before. In order for the part to be oriented along the x-axis, I want to start with a section defined in the YZ plane and then extrude it in the x direction. So within the design modeler, you're really always working in one of 2 modes, either modeling, which is what you see here, or sketching. So we're going to use sketching when we're defining a sketch and modeling when we are creating entities. So in order for me to do my extrude, I would like to define a sketch on the YZ plane. So in the toolbar menu, you can see here I have my 3 planes, XY plane, ZX plane, and YZ plane. So I can select the plane from here, or I can define a new plane. But for now, we just want to sketch on the YZ plane. So I'm going to make sure that my YZ plane is selected. It's selected here on the tree outline. And then I want to go to this blue icon that says new sketch. So I'm going to click new sketch. And you see the new sketch is under the YZ plane. So it's a child of the YZ plane. So we're going to sketch on the YZ plane. In order for us to better see it, I'm going to select the x-axis. So now I'm looking at the YZ plane. And my section is simply a circle that has a diameter of 0.21 inches. Looking at my scale, it is still in meters. So I want to make sure to fix my units. I go to units and change that to inches. Looking at the scale again, I see 100 inch. This is really too much. So I'm going to zoom in. Okay, now we are looking at a better scale. And we are going to start sketching. So I'm going to go to sketching mode. And in the sketching mode, in the sketching toolboxes, you can select to draw, to modify, to assign dimensions, to use constraints, and to do here the settings. So what we want to do now is to basically sketch a circle. So I'm going to go to draw, and I'm going to select circle. I'm going to go to the graphics area, and I want to show you here as I move my cursor anywhere, I don't see any letters showing up. If I get closer to the axis, I start seeing a letter C. It's not, it is 90-degree rotated, right? So if I come here close, you see like this is showing here. If I click there, my center of the circle is going to be constrained to the axis. If I move close to the origin, right at the origin, the letter that is showing here becomes P for a point. And we want the center of the circle to be constrained to the origin. So I want to make sure before I click that P is showing, I do a left click and move out to get a radius of about 0.21. Here is a circle that is showing in a light blue color because this circle is not completely defined. I did not specify or did not assign a dimension. So I want to add a dimension, which is the radius of the circle. So I click radius and select my circle and move here. So now I added a dimension, which is radius R1. If I look in the detail view of my sketch, R1 is coming as 0.21507. I want to come here and edit this. I want my radius to be 0.178412. Enter. So that's the radius. I'm also going to change the name of the sketch from sketch 1 to cross section of the part AB or section AB. So this is my sketch here. I think I'm done with the sketch. If I toggle to modeling, you see here cross section AB came, but it is still showing in yellow because I never generated the sketch. So if I click generate, the color changed to blue, and now I have my sketch done. If I show that, select the sphere to show a 3D view. You see here, the sketch is in the YZ plane, and now I'm ready to extrude it. So I'm going to go to extrude. Under the modeling, I get details of the extrude 1. This extrude 1 is really going to be for the part AB. The geometry that I'm using is that sketch called cross-section AB. And I'm extruding in the normal direction. By default, it wants to extrude it 12 inches. I want to change the 12 to 10 because the length of the part is only 10. So on the graphics window, it is showing how I'm going to extrude, and it's showing here the 10 inches. If I like that, I'm going to click generate, and here comes my 3D part. And this is a real 3D part. There is no rendering. It's not like I have a line and I'm adding a section. It's a true 3D part. Question? How do we make what? The sketch. Okay, sure. I will repeat that step. So in order for us to define a sketch, I selected the YZ plane, and I went and selected a new sketch. So I have here a new sketch. It's called sketch 2, right? So I pretend I need another sketch, sketch 2. And I selected the x-axis, so I'm looking on the YZ plane. I toggled to sketching mode, and I selected a circle. I made sure when I was sketching a circle that I start where I'm seeing this letter P, meaning the circle is constrained to the origin. I used a right click and I sketched my circle. Are you able to do that far? Next, I went to dimensions and selected a radius. I select the circle to add a radius dimension. Does that answer your question? Then you can edit the radius right here. You got it? Okay, so now we have the first piece, AB. And when I did my extrude to create the body, the operation here was to add material, which is absolutely fine. This is like when we were doing the lines, I can use add material or add frozen. We still need to create the other piece of the body, which is BC. And BC starts where AB ends at point B. So I want to be able to have a section defined on a plane here. In order for me to do that, I'm going to have to define a new plane. So I want to create a new plane other than YZ, XZ, or YZ. So if I come here and select this icon, it prompts me to a new plane. That's one way of doing it. Or I can go to create and choose new plane. Right? So I can use the toolbar icon, or I can go to create and select new plane. So here I have a plane 4 that is not yet defined. So if I select plane 4 and looked at modeling here, the type is what we're doing here is a plane called plane 4. The type, it says from plane. I can do it from plane, or easier, I can come here and say from face. This would allow me to select a face and create the plane using that face. So we can do that, and it's prompting me to select the base face. So I'm going to select, come here and select this face and say apply. Now I'm going to go generate, and here comes my plane 4 using the face where point B is. I'm going to use that plane 4 to define a new sketch. So I select plane 4. I can select it from here as well. Are you all following? And I'm going to go new sketch. So I have a sketch that is child of plane 4. So we're going to be sketching on that plane. In order to better see it again, I'm going to select the x-axis. So now I'm looking at plane 4. We can see the old section for the part that we've already created, but now we want to have a new sketch. So I'm going to go to sketching, and I'm going to create or draw a circle. Again, I want to make sure I see P. I click and move out. And now this cross section is slightly larger than my earlier section. I'm going to click. Next, I want to put a dimension. So I'm going to go to dimensions and select radius and assign a radius to my new sketch. This came as 0.31877, which is larger than what we want it to be. So I'm going to come here and edit it. So I'm going to put 0.21851. Enter. If I go to modeling, this is sketch 3 that we're working on. And we want to extrude, do an extrude and use sketch 3. So if I go make another extrude, it is asking me for the geometry. I can select it here, or I can simply come here and select sketch 3, the same thing, and say apply. We are going to extrude in the normal direction, and this time we want to extrude it 12 inches. I encourage you all to keep working with me. If you can follow this example, you'll be able to finish homework 7 in few minutes. So as much as possible, try to keep working with me. If you have any questions, please stop me. So this is extrude 2, which is really going to be the piece BC. I go generate, and here comes my second piece. We want to look at it in the XY plane. This is what you see. AB and BC. We are happy with our geometry. I'm going to save the project. So I go like save. So this is updating the project, even in Workbench. You see here saving in Workbench. It says save project. Once it's done saving, I have material and I have geometry. I'm ready to move to the next step, which is to create a mesh within mechanical. So I'm going to go to model and double click the model, and this will start mechanical. Here comes my geometry in mechanical. So I have one solid piece. When I select the solid piece and look at the properties, we have here under the definition of the details of the solid, a material, and it says the assignment, and by default, it used the structural steel. So one of the first things I want to do is make sure that my part has the correct material assigned to it. So I'm going to select structure steel and make sure to apply class material. So this solid part is made of class material. Before I move any further, I want to check my units. Looking here at the ruler, it's showing the units in meter. So I want to go to home and units and make sure I select US customary, inches, pound mass, pound force, etc. All right. Next, we can go to the mesh. And when I look at the mesh menu, I can just simply click generate to come up with a mesh. Now, because we do not have any line concepts, ANSYS would know that we're not using any beam elements, but we rather have 3D geometry or 3D CAD. When it breaks it into pieces, it has to use one of its solid elements. And by default, it's going to go with tetrahedral elements. So if I come here, whether I select generate or right click the mesh and say generate mesh, it is automatically going to start breaking this into tiny pieces. And by default, these pieces have certain sizes as long as they fit within the geometry. And clearly, my part is no longer having these smooth, nice surfaces on the outside. But we're going to accept the default mesh, whichever mesh we get, and see how this is going to affect our results. So now I have a mesh, we have elements, we have nodes, and we are ready. We can now start writing the element stiffness matrices and assemble the global stiffness matrix. But in order to have a solution, we need to define boundary conditions. Otherwise, my matrix is singular and there is no solution. So I go to static structural. And I look at my part, and my part is fixed at point A. So it should be fixed here. So under the environment menu, I have supports, and specifically, we're going to fix it at the left wall. So I'm going to say fixed, and I'm going to select a face, not a point, not an edge. Remember, when we modeled that using beams, we only had to select a vertex because the vertex represented a face. Here, when we are working with solids, I need to select a face. And I go apply. So we applied a fixed support on the left face. Any questions so far? So this is the fixed support at A. Of course, we can come here and rename it if we want and say fixed support at A. On the other end, we had the wall at a distance of 0.002 inches, correct? So I'm gonna go to the other end, look at the other face, and I'm gonna go to supports, and this time I'm gonna pick displacement. This is like a prescribed displacement. I'm gonna select the face and go apply. I have X, Y, and Z components. In the X direction, I have this 0.002 inches. In the Y direction, I'm not going anywhere, so I put it to 0. And in the Z direction, I'm not going anywhere, so I also put 0. This displacement is at C. So we have fixed support at A and displacement at C. Next, we're ready to apply the load. And the load was applied at B. And I want to look here a little bit at B. So when we focus here, if you have this part in real life and you want to load it at B, how would you load it? On the little ring, yeah, maybe at the most, like put a flange or attach it to it or a bracket and then load it. But you really want the load to be distributed over that surface. Because this is symmetric, really the point of action, if you're trying to find an equivalent load, will be going into the center. But there is no way we can go right inside and apply the load in real life. And this is one of the beauties of having a 3D model, because I can better mimic what's happening in real life. So when we want to apply the load, we're definitely going to apply it to that face here, right? And I can simply apply it as a force. So I come here and select a force, and the geometry, I apply it to that face that I selected. We are going to define it by components like we did before. So I have a type as a force defined by components. And I have X, Y, and Z components. The force is a 1,000 pound force in the X direction, and I have 0 in the other directions. So this takes care of my 2 supports and my load. Let's check if we have a solution. Solve. Okay. Building the mathematical model. Now, can anyone count how many elements do we have this time? Estimate. More than 100, right? And imagine each of these elements have like 4 nodes, at least, more than that. So you can imagine we have thousands of equations. I'm going to show you in a second how many of them do we have. That's why it's taking time here solving a mathematical model. And this is a tiny little part, nothing special. And we even have a mesh that is not fine enough to capture the behavior. So we, by all means, do not want to do or solve this problem by hand, right? Okay, so yeah, I got a check mark, so we have a solution. The first thing I like to do is to look at the behavior. Is it really doing what I expect it to do? So I go to solution, and I'm gonna define, look at the results, and I'm gonna go to deformation and look at the total deformation just to get a feel. So I want to solve for the total deformation. Let's look at this. Here is my part. If I play the animation, starting with the horizontal part, and as it gets deformed, it also gets distorted. We should expect this to only be moving in the X direction. But you want to be careful because these animations, of course, are magnified. So if I want to look at it more carefully, I can start looking at X components and Y components and see how much really the Y component is. Now, from our memory, we know that we got a maximum displacement of about 0.0055 or 56. Here we're getting 0.0065. So that's a bit more than what we expect. Maybe we have like a 10% error, right? Okay, so let's come here and I'm gonna select total deformation and say duplicate without results. And I'm gonna do that 2 times. You're gonna see why. So the first duplicate, I'm gonna change it from total deformation to directional deformation. And I'm gonna select the X-axis. So that's the first one. I'm gonna select it and do a right click and select rename based on definition. Should change the name to the X-axis directional deformation. The second duplicate, I'm gonna select it and I'm gonna change total deformation to also directional deformation. And this time I want to look at the vertical direction. So I'm gonna check the Y-axis. And I'm gonna solve. Oh, before I do that, let me rename based on definition. So now I have X and I have Y, and I'm gonna go solve. Okay, so if I look at the X-axis, I'm getting a 0.0059 maximum displacement, which when we did it by hand, we got 0.0056. So we're not totally off in the X direction. If I look at the Y-axis, this should be really 0, but I'm getting a very small 0.001. So the point I'm trying to make is still capturing the main behavior, but there are these errors that are contributing to a deflection in the Y direction. And we're going to see later how we fix it. But let's look at the other results, and then I'm going to show you how we can take care of that. Remember, this is a numerical method. When I break the part into pieces, I do not have perfect pieces to fill in the geometry, especially with the mesh size that we looked at. So this is going to contributing to the error. I no longer have a nice symmetrical part that when loaded is going to continue to move in the X direction, but it gets distorted partially because of the mesh. The problem asked us to find the wall reaction. So I'm going to go to the solution and I'm going to use similar technique by going to probe and selecting a force reaction. For the wall at A, I'm going to select fix the support A. And then I'm going to go to probe again, select force reaction. And now I want to find that at C. So I'm going to select displacement C. So I have a force reaction and force reaction 2. I can come here and rename it to force reaction at A. And the second one, I'm going to rename it to force reaction C. Oops. No. So I have a force reaction at A, force reaction at C. We also wanted to find the displacement at B. So we wanted to find the displacement here. Now again, if I want to find the displacement here, I better not select the edge, but I want to select the face where we applied the load. So I'm going to come probe and do deformation, and I want to select this face, apply, and we really wanted to look at the displacement in the X direction. I can come here and rename based on definition. We're looking at X-axis deformation. I can rename that, and instead of all of that, I will put deformation at B. Okay, let's check these first. I'm going to go like solve, and let's look at the force reaction at A. It is a pull force, and if I go down here in the details, I'll find that the magnitude is 548 pounds. When we did it by hand, we found 555. So if you look at the percent error, 7 divided by 550, still we get some decent results, very small percent error. If I look at the force reaction at C, the wall at C is pushing back, and the magnitude is 451.45. When we did it by hand, we got 444. So again, we have 6 pounds difference. If I look at the deformation at B, I'm getting a 0.0059 instead of 0.0056. Next, we want to look at what's going on within the member. Now, I no longer have beams, so I really cannot look at internal forces. However, the reason we looked at internal forces because we used the internal forces to find stresses. When I'm using solid elements, I can look at the stresses directly. I no longer have a beam tool to use, but I can go here to solution, results, and you can see now my strain, my stress options, they're all available to choose from. So I can come here, and we know that this is an axially loaded part. So what we are looking for would be the normal stress. So I can come here and select normal stress. And I can solve. And look at this. Clearly, we have almost the same color throughout AB and the same color throughout BC. If I want to get a feel about the stress levels, I can go select probe and go anywhere within the member. I do not want to go to the edges because at the edges, we have some stress concentration due to the change in the geometry. But within the member, you see it's all in tension, and pretty much I'm getting 5,500 PSI, positive. If I go select the other part, it is all negative, and I'm pretty much looking at 3,000 PSI. And again, there is variation. It should be the same number throughout. But at least we were able to get the result just by using the default mesh. Now, I'm blaming some of the discrepancies due to having a mesh that is not very fine. I can show you the effect of the mesh. I don't want you to worry too much about it. For the most part, we can use the automatic mesh generator without having to make changes in this class. But when you practice and you use finite element, you want to make sure you have a good mesh. And in this little example, I'm going to demonstrate the importance of having a fine enough mesh. So I'm going to go back. Oh, before I do that, let me go to solution information. and show you how many elements we ended up using. I think you would like to see that. I want to show you here the total number of nodes is 1,612. This is using the coarse mesh. I'm still going to refine my mesh. The total number of solid elements are 716. So how many equations did ANSYS have to solve for? Now, I don't expect you to have to worry about the details of the solution. I'm just demonstrating here to give you an idea. So again, the number of nodes, 1,626, 748 elements. Here is the type of elements, 716. You see the element type or name in ANSYS is called solid 187. You ended up with 4,752 equations. When we solved one problem by hand, and it took us like 2 pages of work, we had 4 equations. So I'm sure none of us wants to attempt this by hand, right? Okay, we're not happy with this, and we think the mesh is a bit coarse, or at least we don't have a very nice mesh. A simple way of getting a much finer mesh that I'm going to do is by changing the default size of the mesh. So I pick sizing. And I want to make sure to select the solid part. I do not want to pick on surfaces, but rather pick the solid part. So I'm going to go to the geometry, and it says no selection. If I leave the smart select, I'm basically trying to select like a vertex or a face or an edge. So if I come here and select, it would select the face. But in order to make sure I'm selecting the solid part, I'm going to enforce a body selection. And I'm going to come here and select my part and say apply. So now, oops, apply. So now I have one body selected. If I look at the element size, the default goes to 1.097 inches. I'm going to come here and change that to only a 0.1. All right, so like 10% of that size. So what is this going to do? This is going to force the automatic mesh generator to use smaller size elements. Of course, if I use smaller pieces, I can better fit them within the geometry to still keep the geometry more or less as we like it. Now, you see the flash icon. Because I messed my mesh, I'm ready to regenerate or create a new mesh. So I'm going to go generate. And see, ANSYS now is going to take time to create a mesh. But look at this mesh. What do you think of that? You remember all the crooked faces we had? Look at this. Isn't that a much nicer mesh? Okay. Is this going to affect the behavior? Let's check. So I'm going to have to run my solution again. And let's try to keep an eye how much time this time is going to take. So I'm going to select solve. Solve. Okay, ready. Creating solver input. I'm going to have to wait this time. 2%. Oh, you're using your computer? Yeah. Right. And that's why for this class, I don't want you to worry much about refining the mesh. I'm mainly demonstrating here. 10% building the mathematical model. 26% preparing mathematical model. You see how slowly it's going? And this is one small part. Imagine if you're modeling a huge system or an assembly with several parts. 100% writing results file. Almost there. I hope you will be happy. All right, we have a solution. First thing I want to look at is the total deformation. Look at this now. Oops, sorry. Okay. So look at my parts and let's play the animation. You see how the fine mesh solved many of the issues we had. Look at the maximum displacement. And I'm even looking at the total. Clearly, I have this 0.0056, which is what we got when we did it by hand. If I look at the x-axis, 0.0056. Look at the y direction. This is technically a 0. So I really do not have this distortion that we had earlier. Let's look at the force reaction at A. Now I have 550, almost 4 compared to 555. So the error has significantly been reduced with the finer mesh. So I look at the reaction at C, 446. By hand, we got 444. If I look at the displacement at B, I get 0.0056 versus 0.055. If we look at normal stresses, and look at this, please. Yes, of course, there is a discontinuity here. But everywhere else, if I take my probe and start looking at the numbers, consistently, I'm getting 5,500 and almost 36 throughout tension. This is way more consistent than before. If I look at the other piece, compression, minus 2,975. The finer mesh has reduced the percent error. Can we always afford to go that fine when we have bigger parts? Not really. But this is just to demonstrate that you want to make sure you use a reasonable size mesh such that you're not compromising the solution. With this, we were able to answer all what we were asked to find. But again, I emphasize, I do not have an option to look at a normal force because I'm not using beams. I'm using solid pieces. So all what we can do is to look at stresses, we can look at strains, we can look at displacements. We can even look at the state of stress, like use that to calculate at any point. I can calculate a von Mises stress, calculate the principal stresses, look at the shear stresses at any given point. So if you go to solution, go to results, go to stress, you see here I can look at maximum principal, equivalent stress, minimum principal, maximum shear, just the shear stress. So you can look at all these, even bending stress, you can look at all these types of stresses here since we are using solid elements. You can also look at the strain, and you can look at the maximum principal, maximum shear, an equivalent strain as well can be looked at, right? Question?
Can you go over how you did the force reactions again? Mine's coming up with the red, like,
Okay. When you, I'm going to go back here and pretend I'm redefining it. So when I go probe and choose a force reaction, please make sure to keep the default location method as boundary condition. When you do that, you want to select for A, I want to select the fixed support at A. And then I need to solve. So I solve here. and I get a force reaction. Is that what you're doing? Or were you able to fix it?
It's what it says on here. I'm just gonna redo it. I played around with
You may have accidentally changed the location method, and that's what caused the problem. Okay. More questions? I want you to, as soon as possible, apply what we learned today to homework 7, which is the very same problem. If I go to the assignments, we have homework 7. This is the very same problem that you have done by hand calculation. You've done using beam elements, and I want you to do it completed today using solid elements. This is very similar to the class example. You have 3 extrudes instead of 2. You have 2 walls, so it's fixed at 2 ends, and you also have 2 loads. So please complete this using solids. Make sure that you are getting results that are comparable to what you got earlier. This is due tomorrow by midnight, and that should give you a full break with no homework assignments, no quizzes to prepare for. And then we're going to come back on Tuesday. Of course, I always encourage you to attempt homework 8, but I'm also going to be going over that in class on Tuesday. So if you start on it, you'll come to class prepared to ask questions and learn more. I would like you to at least get the CAD created, the geometry created. So when we come in class, you can learn the little things that are left and get the homework done as well. Okay, we are going to have a quiz on Thursday after the fall break. So like 10 days from today, 9 days from today. And this is going to be on ANSYS using beam elements only. Right?
So no solid.
No solids for the quiz because we are just practicing solids. I always like to make sure you have plenty of time to practice before we take a quiz or an exam. Good. Enjoy the break. Stay well, safe, and healthy. And I'll see you when you come back on Tuesday. Thank you.
when you're applying the fixed support, is it the edge or base or like?
No, you